lab on projectile motion. So a quick introduction. The purpose is to analyze the motion of a projectile and compare it to two computational models, one which takes into account the drag force and one which doesn't. The object is the same as the system, which is a piece of crumpled paper, and then the surroundings are the air and earth, which create the forces that are acting on the paper. I use Tracker to model the software for the observed or experimental position, and then I use GlowScript to model the software as my modeling software for the the predicted position. This lab should demonstrate Newton's second laws as well as the effects of drag force. What is Newton's second law? It states that the net external force equals the change in momentum of a system divided by the time over which it changes. So that's demonstrated by this formula, and then from that we can also derive this formula, the velocity update formula from it. What is drag force? Drag force is the force that opposes motion of an object through a medium such as air or water. In this case it's air, so we have air resistance, and it always opposes the direction of motion. So here's the formula for drag force. So here's my actual experiment. This first photo here, you can see where it starts, and then this is the next position, and this is the next position. Well, there's more positions in between, but this kind of shows like the trajectory of the paper ball that was thrown through the air. And then here, this initial position is straight from here, from Tracker. So yeah, here's my initial position. My initial velocity, I had to use this formula and do this math for both the x and y components. You can see that here I did the second position minus the first position, and then I divided it by the change in time, which was 0.017 for both x and y. And then I did this separately for each component in order to get this as my initial velocity, so roughly -2 and -0.47. Yeah, and here are my charts that show the motion. This is my computational model now, which is on GlowScript. My mass of the ball is pretty small since it's just a small piece of paper, and then this is gravity, the little g, and then b is the proportionality constant for drag force. So I ran it once when b was 0 to model no drag, and then once with b as 5 to model drag. And then t is the time over which the whole entire video occurred, which here, the whole video took 0.267 seconds. So I input that here in order to match the Tracker model. And then here is where I use the drag formula in my code. And then down here, I use the position and velocity update formulas in my code. And then these are the results of my code. So you can see it looks pretty similar to the path from Tracker. So this is from my model, and this is from Tracker. And then this is also that same chart. And then here you can see how the y position changes over time. That's why these two graphs look like they're kind of flipped of the other one, but that's just because they're over time rather than over the x-axis. So instead of showing the actual position, it's showing how y is changing, which is what we're mainly looking at. And you could also see that this GlowScript chart looks pretty similar to the Tracker chart. So here are my final results, where I combined all of both of these charts onto one. So blue is my GlowScript model without the drag, red is my GlowScript model with the drag, and then yellow here is from Tracker. And then here's a small sample of some of the data I used in order to create this chart. You can see it's pretty similar. Each of the lines are all pretty close to each other. So my model did pretty well. Possible errors. Ball shape is possible error, causing some weird air resistance patterns. Position tracking and video angle also could have caused errors just because it's a human doing this and tracking each position. I think the most likely error is the error with the coefficient of drag, because as you can see, it's super hard to tell the difference between the red and the blue. They look super close. So the model with drag and the model without drag, they look so close. So I think that's where there's likely an error, because you can't see that very well on my chart. Further questions. What would happen to the terminal velocity if the object were thrown downwards? The answer is that it would not change. That's because it's only based on the magnitude of the drag force being equal and opposite to the gravitational force. So basically the terminal velocity would just be reached faster. And yeah, what does this all mean? So basically this just does what we were aiming to do in showing how projectile motion works and how Newton's second law factors into it. And most of all, it shows how gravity and air resistance affects projectile motion. So yeah, thank you.